Yesterday, we talked about some basic shapes you guys have been introduced to before, which were geometries based around a trigonal planar arrangement of atoms, or linear, or tetrahedrals. Okay. We also introduced the idea of trigonal bipyramidal geometries. Today, we're going to continue looking at things that are based on trigonal bipyramidal electron pair geometry and also octahedral electron pair geometries. Okay, which are a little bit more advanced. After that, we're going to do a whole lot of examples. Then we'll have time to start the assignment here in class, which is here on the board. And for those guys who are not here with us today, I'll just remind you that it is problem 64 to 71, 73, and then 74 as well. Okay. Was in biology late. Who's assigned by? Okay. Excellent. Very good. Okay, so that's the homework for tonight. Okay, so let's just kind of start back a little bit from yesterday. Yesterday we introduced the trigonal bipyramidal geometry, which happens, or which you will see when you have 5 pairs of electrons around the central atom. The reason why you get this weird geometry is because the electron pairs repel each other. They want to be as far away from each other as possible, and they will distribute themselves around the central atom in such a way to minimize the repulsion in between them. Yesterday, we used the example of phosphorus pentafluoride, PF5, as being our stereotypical example, where we have phosphorus here in the middle, bonded to each of the fluorines. Okay? And of course, each fluorine's got its full octet of electrons, so I'll put dots around each of those guys, like that. Okay? So for this molecule, the electron, I'm just going to say the EP geometry is going to be trigonal bipyramidal. Okay? Now, the reason why the electron pair geometry is trigonal bipyramidal is because the electrons really are what determine the shape, right? They are arranged in such a way to maximize the space in between them. Okay? Now, what's weird about this geometry is that you have basically 2 sets of electrons. You have these guys here, which I told you guys yesterday, these are called equatorial. Okay. Those guys there are called the equatorial ones. These guys here are called the axial positions. Okay? Now, what's kind of weird about this geometry is that there's a 90-degree separation between these guys here, but if you look at the ones here that are along the equator, there's 120 degrees of separation in between those guys. So it's kind of a little bit weird and interesting. Okay? For this molecule, the molecular geometry is also trigonal bipyramidal, and the reason why they are the same here is because all the pairs of electrons on the central atom are used to make bonds. They're used for bonding. There are no lone pairs of electrons anywhere here in this molecule. And there we go. You guys remember that from yesterday? Okay. Now, just like we looked at tetrahedral geometries, and we saw that there are different forms of distorted tetrahedral geometries, in the same way, we have distorted trigonal bipyramidal geometries that it's worth being aware of. Okay? So I'm going to show you guys those right here. Those are summarized here on this slide. I'm going to draw a couple examples of each, or one of each of these types here. So let's consider the molecule SF4, for example, okay? And say that I want to draw this guy's Lewis structure. How many valence electrons do I have total to work with in this molecule? Let me call on a victim to answer that question for me. How about Ben? How many total electrons will I have in the sulfur tetrafluoride molecule? 34 valence electrons to work with altogether, okay? Now, if I draw the Lewis structure, the central atom is going to be my sulfur, okay? This is going to be attached to 4 different fluorine atoms, okay? And, of course, these guys are going to have their full octet. So we're going to place electrons here, electron, 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 like that, okay? Altogether, I've placed 32 electrons. How many do I have left? We have 2 electrons left. Where am I going to put those? We're going to put those on the central atom, which is the sulfur right there. That is absolutely 100% correct, okay? Now, when I do that, sulfur is violating the octet rule. Is that okay? Yes, okay, that is all right, because sulfur is in the 3rd period and below and can accept additional electron pairs. So this is totally fine, okay? Now, if I look at the geometry of this molecule, the electron pair geometry is going to be trigonal bipyramidal. And the reason for that is because if I look at the central atom, there are 5 pairs of electrons around the central atom. They want to space themselves out to be as far away from each other as possible. the way they can achieve the maximum distance in between them, in between each other, is to adopt the trigonal bipyramidal geometry. But if I look at the molecular geometry is what we call a seesaw. Okay? Because it's shaped kind of like a seesaw. You can imagine, guys, if this is my regular trigonal bipyramidal molecule right here, okay? If I lose one of these fluorines, okay, so where I've only got 4 bonded fluorines, I still got my electron pair right here, okay? But if I look at the shape that the other atoms here define, that looks kind of like a seesaw if I turn it like that, right? And in fact, yeah, I know. Yes, the simple things, right? Chemists also are easily amused. So there we go. We still have this lone electron pair here, though, which is occupying space, which is why it adopts this kind of geometry, why these guys don't spread out more, okay? Now, if I look at the bond angles here, okay, just like with our distorted tetrahedrals, okay, what is this lone pair of electrons going to do to the bond angles? It's going to push these guys close together. These guys are going to get pushed close together. So this bond angle here, we say is going to be less than 90 degrees, because in the perfect trigonal bipyramidal is 90 degrees. This bond angle here is going to be less than 120 degrees. Do we know exactly what the measure is going to be? No. The only way to know that is to do an experiment, okay? But you can predict that these bond angles will be distorted by the presence of that lone pair of electrons. And you would need to be able to, for the test, specify this bond angle is less than 90 degrees, this one is less than 120 degrees, and you would need to specify why that is the case. Okay. So that's the seesaw shape. That's a trigonal bipyramidal electron pair geometry where we're missing one bonded atom. Okay? What if we take off another one? What does this look like now? Like a T. Exactly. Okay, so if we're missing 2 bonded atoms, but we have 5 pairs of electrons, we get a T shape. An example of that would be ClF3. Now, what strikes you as strange right away about that molecule? We got a chlorine as being the central atom. Bizarre, but it happens, okay? Here we go. We're going to have our chlorine here in the middle, okay? We're going to have a fluorine, and a fluorine, and a fluorine. Now, if I look at this molecule, ClF3, we should have a total of 28 electrons to place, okay? If I fulfill the octets of my fluorines here, how many electrons do I have left? I got 4 left. Those go on my central atom, if I have electrons left. Now, chlorine here is breaking the octet rule. Is that all right? Yes, because chlorine is in the 3rd period and below and can break the rules. Okay, so here we have 2 lone pairs of electrons, and we have 3 bonding pairs. Because there are 5 pairs of electrons altogether around the central chlorine, it is going to be a trigonal bipyramidal arrangement of electrons. So the electron pair geometry, if you were asked, would be trigonal bipyramidal. Okay, but the molecular geometry is going to be, in this case, a T shape. Yep, a T shape, because that's what's left, like this, okay? The way I have it drawn like that, it kind of looks like that way, but if you turn it like that, it looks like a T, and there we go. Okay? The last distorted trigonal bipyramidal we're going to look at is something like xenon difluoride, XeF2. Now, what's weird about this one, guys? Xenon's a noble gas, but this can't happen, okay? If we draw the Lewis structure, if we figure it out, okay, we should have 14 plus 8 is like 22 electrons altogether, okay? We got a bond here to a fluorine and a bond here to a fluorine. If we fulfill their octets, how many electrons do we have left to place? Six, okay? So we're going to go 2 here, 4 here, and 6 here. So here we have 3 lone pairs of electrons. And there we go. The electron pair geometry around this molecule is going to be trigonal bipyramidal. Why is that? It's just the way it is. Yes, I like that answer. There are a lot of things that are just because that's the way it is. But the reason why is because there are 5 pairs of electrons around the central atom. They want to be as far away from each other as possible. So the electrons adopt, woohoo, all right. The electrons adopt this trigonal bipyramidal geometry to maximize the space in between them. Now, we only have 2 bonded atoms, okay? So if we look at what's left here, guys, here's my trigonal bipyramidal. I'm taking off my last atom here. We only got 2 left. What kind of shape does it look like to you? Linear. And there we go. So that's what we're going to have. We have a linear molecular geometry. Why wouldn't it be bent? Well, that's a good question. Okay, so why doesn't it do this instead? Okay, That is an excellent question. Okay, the reason why is because you remember these electron pairs all repel each other, right? Okay, but which ones repel more? The unpaired, the non-bonding electrons, right? So really, the most energetically favorable thing would be is if these guys are as far away from each other as possible. Here they're 120 degrees apart. If I move this guy like this, now they're 90 degrees apart. Not as good. They're close together, so they repel more, and so that's the more favorable geometry, and that's what it adopts. Yeah.
Trigonal bipyramidal for the electron pair.
Uh-huh.
Like it's always five pairs of electrons.
Uh-huh. Always 5, yeah. So just having the 5 pairs of electrons around this guy means they adopt a trigonal bipyramidal geometry, okay? Now, what the molecular geometry is just depends on how many atoms you have attached, okay? So we have 2 atoms bonded, it's linear. If we have 3 atoms bonded, then the molecular geometry would be T-shaped. If we have 4, then it becomes a sawhorse. If we have 5, then it becomes trigonal bipyramidal, and there we go. Okay. Any other questions, guys? We'll practice. This will make sense. Okay, next, we're going to look at the last basic shape, which is octahedral geometries. You will get octahedral geometries if you have 6 pairs of electrons all around the central atom, okay? Now, the reason this baby is called an octahedral molecule, here's a model that I built right here, okay? The reason this is called an octahedral is because if you can, like, imagine that each of these atoms was attached to each other, okay, if you drew an imaginary line connecting each of these guys, the shape you would define is a regular octahedron, okay, a shape that has 8 equal triangular faces, much like an 8-sided die, okay. Yeah. What? An 8-sided die? Yeah, it does. It looks exactly like an 8-sided die. I'll show you one tomorrow. Okay. This is an octahedron. A good example of an octahedral molecule is SF6, sulfur hexafluoride, okay? Where sulfur, yes it is, it's possible, where sulfur is a central atom, it's attached to 6 fluorines, like so. If I total it up in this molecule, we should have, from the fluorines, 42 valence electrons, 6 from the sulfur, so we should have 48 electrons altogether. If I place my 6 electrons here around each of the fluorine to make them happy, it ends up that I use all the electrons. Now here, how many valence electrons does the sulfur have attached to it? It has 12 altogether. Is that okay? Yes, because sulfur can break the rules. That is totally all right, okay? So this turkey, the electron pair geometry is octahedral. The molecular geometry is also octahedral, because all the pairs of electrons are bonding pairs of electrons. Does that make sense, guys? Okay, now, in just the same way that we had distorted tetrahedral geometries, and we had distorted trigonal bipyramidal geometries, we can also have distorted octahedral geometries. Okay, let's take a look at the most common ones. An example. Consider the molecule BRF5, okay? If I look at this guy right here, again, this is weird because bromine's a central atom. It's bizarre, but it happens. How many valence electrons do I have total in the structure? 42. Altogether. Now, bromine is going to be my central atom, and it's attached to a fluorine, and 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 attached to a fluorine. Okay? If I place my electron pairs, 8 around each fluorine, I've used 40 electrons altogether. I have 2 left. Where are they going to go? On the bromine. There we go. So there's my bromine. It's got a lone pair of electrons like that. Okay? The electron pair geometry of this molecule is going to be octahedral because there are a total of 6 pairs of electrons around the central bromine atom. However, there's only 5 bonded atoms. So if I take this guy off down here, okay, what does that shape now look like? A square pyramid, like it says on the slide, exactly. This is now, the molecular geometry is square pyramidal because I've lost this bottom atom. This is just an electron pair here. It is occupying that space, okay? But if I'm looking at the shape defined by these atoms, it is going to be square pyramidal. And there we go. So you would say that the molecular geometry here is square pyramidal. Okay. Now, did I tell you guys that in the normal octahedral molecule, the bond angle's 90 degrees? Okay, well, if I didn't, they're all 90 degrees. That's kind of neat. These are all 90 degrees. That's 90 degrees. That's 90 degrees. That's 90 degrees. And that's 90 degrees. And whatever, okay? And my square pyramidal molecule right here, where I have this lone pair of electrons, what's the bond angle going to be? It's going to be less than 90 degrees. And this is going to be less than 90 degrees because the geometry is distorted by the presence of that lone pair of electrons. They're all pushed closer together. Does that mean that we know exactly what the bond angle is? We do not know exactly what it is. We just know that it's less than 90 degrees. You will need to be able to explain why on a test. Let's look at one more, okay? We'll look at xenon tetrafluoride, okay? If we look at the total number of electrons we have to build that molecule, we got 36 valence electrons altogether. What is the central atom? Xenon. In the middle, bond to a fluorine, bond to a fluorine, bond to a fluorine, bond to a fluorine, like that. Okay, if we place our electrons, 8, 16, 24, and 32, like that. I've used 32. How many have I got left? 4. Where do they go? On the xenon right here. So we're going to have one pair here and one pair here. These guys occupy space. These guys occupy space. And there we go. Okay? Now, this turkey, once I've lost its other atom, this is called a square planar molecular geometry. And the reason why is because I have these 4 atoms, and they're all in a plane, and it makes a square. Pretty profound. Okay. For this molecule, what's the electron pair geometry? It is octahedral because it has 6 pairs of electrons around the central atom. The molecular geometry, on the other hand, is going to be square planar. Okay. Give me a thumbs up if this all makes total absolute sense. Kind of, sort of. What we need now is practice. Lots of practice. But before that, a quick word about this lovely, awesome, and amazing chart that I gave you guys in your notes. Oh no, dude. Touch it all you want. That's fine. You print this off for you to do with it what you want. If you want to make it into a paper airplane and throw it around the room when we're not having class, that's fine. I don't care. When we're not having class, don't hit me in the eye with a paper airplane. That would be terrible. Okay? Here's how to read this thing. Okay, here it says steric number. A better way to think about this is kind of scratch that baby off. Okay, that would be effective electron pairs. Okay? If I have 2 effective electron pairs, that gives me a linear geometry. Linear electron pair geometry. If I have 3 effective electron pairs, that gives me a trigonal planar electron pair geometry. If all 3 of my bonding pairs or electron pairs are bonding pairs, that means the molecular geometry is trigonal planar. So I just want to write down here, okay, so we have 3 effective pairs, okay, that means it's going to be a trigonal planar electron geometry. That's terrible handwriting, but you guys get the idea. Anything that's got 3 pairs of electrons is going to be a trigonal planar electron pair geometry. Anything with 4 pairs of electrons is going to be what? Tetrahedral. Anything with 5 electron pairs is going to have what electron pair geometry? Trigonal bipyramidal electron pair geometry. Anything with 6 is going to be what? Octahedral. Okay? And so now what this says, what the chart tells you, is, okay, well, I've got a trigonal planar electron pair geometry. If I have 3 all bonding pairs, no lone pairs, it's going to be a trigonal planar molecular geometry. If I have 1 lone pair, it's going to be a bent geometry. If I have a tetrahedral electron pair geometry, and I have no lone pairs of electrons, the molecule will be tetrahedral. If I have 4 pairs of electrons, a tetrahedral electron pair geometry, and I have 1 of those pairs a lone pair, the molecular geometry is trigonal pyramidal. If I have a tetrahedral electron pair geometry, but 2 lone pairs of electrons are going to be bent, and et cetera, and et cetera, and et cetera. Do you guys see that? Yeah. Pretty legit, huh? Yeah. What? Oh, well, okay. So this would be if all the pairs of electrons are bonding pairs. Okay, so this is like for a trigonal planar electron pair geometry, the basic molecule is a trigonal planar molecule. For a tetrahedral electron pair geometry, the basic molecule, if all the pairs are bonding pairs, is a tetrahedral molecule, and etc. These are all the distorted versions, though. So, like, for example, if we're missing one atom and we have one lone pair of electrons, here this is trigonal pyramidal. If I have, whatever, two missing atoms, two lone pairs of electrons, now you get a bent geometry, whatever. And what's really cool is it even shows you the bond angles on here, guys. Yeah, whoa, I know. Now, you're not going to be able to use this on the test, though. So I recommend that you use this to do your homework with, but do not use it as a crutch. Make sure that you're trying to, as you gain confidence, and after we're done with the examples today and you guys are going on to your homework, use this to check your work, but don't use it to do all the problems. Because if you do, you'll get used to it. And then when you get the test, you will forget. So make sure that you use it to check your work, but not to do everything. With that, do all these examples. Yeah, man. With your partner. I want you guys to do all these examples. We're going to go over them here in a few minutes, but I'm going to give you guys, like, say, 5 or 10 minutes or so. I want you guys to draw all the Lewis structures and predict what are the electron pair and molecular geometries for each of these molecules. No. Leave the spheres and the bonds and everything in the bags. For the first one, fluoromethane. What's that Lewis structure look like?
Central C, and then
3 H's and 1 F, which is what you do not want in chemistry. Okay, it's got 6 dots around it. Okay, the electron pair geometry here is going to be what? Tetrahedral. Make sure, I don't care if you guys use abbreviations right now during the notes, but make sure that you guys do write it out in full on a quiz or test. Okay, what is the molecular geometry? It is also going to be tetrahedral. It's going to be the same thing because it has 4 pairs of electrons and 4 bonded atoms. That is correct. Okay, boron trichloride. Let me call on somebody else. Miranda, what is that guy going to look like? Okay, 6 electrons around each chlorine. Okay, there we go. What is the electron pair geometry for this molecule? Trigonal planar, that is correct. That is correct. Now, it's trigonal planar because there are only 3 pairs of electrons around the central atom. That determines it's going to be a trigonal planar electron pair geometry. What is the molecular geometry going to be? It's going to be exactly the same. It's going to be a trigonal planar molecular geometry because there are 3 bonded atoms. That is correct. Okay, arsenic trifluoride. Somebody else here, yeah.
I have a question. Like, how do you know which way to draw from
Well, okay, so what would the alternative be? Like, what's another way you could draw it?
Straight, it's like how ammonia is drawn.
You mean like having boron, chlorine, or something?
No, I mean like the other way.
Chlorine in the middle?
Yeah, I mean B in the middle, and then Cl, and Cl.
Like drawing it boron,
Yeah.
chlorine,
Yeah.
chlorine. Well, yeah, you could draw it like that. It'd be exactly the same. Who cares, right? Because the way AP chemistry. Okay, the way that you draw it does not affect the shape.
It doesn't?
No, the way you draw it, I mean, who cares, right? As long because it's the electron pairs that determine the shape, right? So if you draw it like this,
How you draw it, it's just...
even if unless I'm asking you to make a physically accurate drawing, even if you draw the Lewis structure like that, it's still going to be a trigonal planar molecule because there's still 3 electron pairs around the central atom. Okay, let's look at the next one. Arsenic trifluoride. My next victim is going to be Gabe. Help me out. Arsenic trifluoride. Has 3 fluorines. Okay. Okay, the electron pair geometry is tetrahedral. Okay, the molecular geometry is, what did you say? Trigonal pyramidal, that is correct.
Wait, is electron pair, is this just count the number of electrons on the...
Well, the electron pair geometry is determined only by the number of electron pairs on the central atom, that is correct. Okay. Next, how about Devin Ricano for arsenic pentafluoride? How's that going to look like? And 6 electrons around each one.
Electron pair is trigonal bipyramidal.
Okay, let's just count this up here really quick. Arsenic should have, if we think about it, this has got 5 electrons. Each of these is going to have 7, so that should be 40 electrons altogether. And that looks about right, okay? So you said the electron pair geometry is trigonal and bipyramidal. And the molecular geometry is going to be what? The same thing, trigonal bipyramidal. That is correct. Okay. How about iodine trifluoride, Jake Jones? AP Chemistry. You tell me. There will be 2. That's correct. Okay. So the electron pair geometry here on this guy is going to be what? Trigonal bipyramidal? The molecular geometry is going to be T-shaped. That is correct. That is absolutely correct. Okay. Next victim is going to be Trent Calcott for iodine pentafluoride. What's that baby going to look like?
Iodine in the middle.
Okay.
With 2 lone pairs of
Okay, so we're going to have our fluorines there, and I'll just kind of fill in the electrons. We got all these guys going to have a full octet. And how many lone pairs of electrons you say?
1 pair.
1 pair of lone electrons right there. Okay, that's going to be occupied some space. What is the electron pair geometry on this guy?
Octahedral.
It's going to be an octahedral. Okay. What is the molecular geometry going to be?
Square pyramidal.
Square pyramidal. That is correct. Okay. Let's go to the next. I need one more page here, guys. Finish this up. Okay. Let's go to krypton tetrabromide KBr4. We call another victim here. How about Haley? What is that going to look like? Four bromines around it. Okay, we have 2 lone pairs of electrons, and each bromine, of course, is going to have its full octets. Whatever. Okay, the electron pair geometry here, Haley, is going to be what? It is octahedral. The molecular geometry is going to be what? Square planar. Okay, what was the other one? KBr2, I think? How about Janice Ho? What's that one going to look like? Okay, we're going to have krypton in the middle with 2 bromines. How many lone pairs? Is it going to be 2? I don't know. Let me figure this out. Okay, we're going to have 14 plus 8. We should have 22 electrons total. Okay, so we got 16 or 8 and 8, 16. So we should have 3 pairs. That's right. Okay. If we do that, Janice, what is the electron pair geometry going to be? Trigonal bipyramidal. And what is the molecular geometry going to be? Linear. That is correct. Okay, last one, guys. Sulfur dioxide. This is actually the most difficult one on the thing. I call upon Joanna Lopper. I choose you. Okay. Sulfur is the central atom. Well, wait, hold on. Are we done?
No, I mean,
And then what? Aha, but let's total this up though, guys. Well, we have 8 plus 8 is 16 plus 2 is 18. No, so that fits, okay? But the oxygens here are happy. What about the sulfur? The sulfur's not happy. So, Jana, what can we do here to make the sulfur happy? Give it another bond. How? There we go. So if we take one of those pairs here, we're going to move that over there. So now sulfur's got a double bond here between the oxygen and that oxygen, and that is correct. Now, does it matter which side we put that double bond on, guys? It does not matter which side we do that on. Thank you, Joanna. Okay. Now, how many pairs of electrons effectively does the central atom have? One.
Like, but then you say the two count.
Oh yeah, this counts as one right here. And so how many pairs total does it have?
Two, like that count. I'm you say with two count. You know what I'm saying? You said that when you.
Okay, when you have a double or triple bond, we have a multiple bond of any kind. The multiple bond, even though this is two pairs of electrons, it only counts for the purpose of structure determination as being one. So this counts as one, this counts as one, and this counts as one. Yeah. So altogether we have three. Okay. So here's the tricky part, guys. With this one, like I said, this is the trickiest one. You have three effective pairs of electrons, okay? Which means that the electron pair geometry is going to be what? It's going to be trigonal planar. Because this guy here occupies some space, right? So really the geometry is going to look kind of like that in real life, right? It's going to be that kind of thing. The molecular geometry is going to be what? It's bent. That's right. There we go. Thank you. Sorry to pick on you.
No, I had that right, but I was.
Oh, sorry. Yeah, I might not have been very, very clear on what I was saying, but there we go. Anybody have any questions on that? Okay. One more thing we're going to look at here really quick. These are simple molecules, and they're simple because they have one central atom. What if we have something that is bigger? Okay. Really quick, we're going to look at geometries of larger molecules. I don't know if it is, but if it's not, just write it on the back of a page or something, okay? So we're going to look at this example here, C3H6. We're also going to look at this one right here, C3H8. This guy here is called propane. This guy here is called propene. You guys know what propane's used for? Barbecues. That is correct. Yes. Okay. So if I draw the Lewis structure of propane, it looks like this. I got a carbon and a carbon and a carbon, and these are each bonded to hydrogens to fulfill their octets. Okay. Now the reason here that I said this is not as simple as things we've considered previously is because we do not have one central atom. We can kind of treat each of these carbons like they are all central atoms. Okay. Now, to clarify what I mean by that, I'm going to build a model here. Okay. It's a poodle. No, it's an insect. It's a caterpillar. I don't know. This is propane right here. Okay, this is a model of the molecule propane. What shape does it look like to you?
Snake.
Yeah. Well, maybe not a snake. They don't really have a lot of legs, but some sort of weird insectoid thing. Okay. If you take a look at it, though, like we just consider this part of the molecule right here. What does that look like? What shape does it look like? Kind of like a tetrahedral. And this one here looks kind of like a tetrahedral. And this one here looks kind of like a tetrahedral right here. Okay. And we look at each of these carbons, guys. How many pairs of electrons does that carbon have around it? It's got 4 pairs of electrons. So the geometry around this carbon atom is going to be tetrahedral because it has 4 pairs of electrons. Yeah, I was like, getting colder, yes. Okay. This guy here in the same way has got how many pairs of electrons? 4. And so this is going to be tetrahedral around this atom here. And this guy here is going to be tetrahedral around this atom here. So for this larger molecule, it's kind of like 3 tetrahedral molecules put together. Okay. So if I asked you on a homework or on a quiz or a test or something, what is this bond angle right here? What would that be?
109.
What? Yes, that magic number, 109.5 degrees. On paper, it looks like 90 degrees, but remember, in space, it's actually 109.5 degrees. Do not be fooled by that. Yes, it is. Now, if I ask you for this bond angle right here, guys, what would that be?
180.
Or rather, that bond angle right there. That would also be 109.5 degrees. These are all going to be 109.5 degrees, these bond angles, because each of the carbons there is going to have a tetrahedral geometry. Now let's consider propene for contrast. I'm going to draw this guy down here. Maybe I'll draw this guy in a different color just for fun. Okay, I'll make this one in red. Okay, the color of correction. Yes, there we go. Okay, now we got a double bond here. Oh my gosh.
Oh my god.
Okay. Nothing? No, nothing is not a good answer to that. No. Nothing, we will fail. No, we will not fail. Okay. Looking at this atom right here, guys, how many pairs of electrons are around this guy? There's 4 pairs of electrons. So this carbon atom here is going to have a tetrahedral geometry around it, right? What about this guy right here? How many effective pairs of electrons has that got? This has only got 3 pairs of electrons over here. Therefore, if I look around the geometry around this atom, this is going to have a what kind of arrangement of electrons? Trigonal planar. Yeah. And if I look at this one right there, guys, how many effective pairs of electrons around that guy? Trigonal planar. There we go. It's got 3 pairs of electrons. Okay. So now if I ask you for this bond angle right here, what's that going to be? 109.5. If I ask you for this bond angle right there, what's that going to be? 120 degrees. Because even though it looks like these are drawn flat like that, in the book it's going to have a 90-degree separation, but in reality, in 3D, it's going to have 120 degrees of separation. Okay? Same thing over here, guys. If I ask you for this bond angle, what's that going to be? 120, okay? Because the geometry around this carbon atom is going to be trigonal planar. And there we go. Does that make sense? Okay. Why do you need to know that? Because the AP test might ask you. Because